Welcome back everyone. In this lecture we will continue to see some basic properties of root system. In particularly we will try to classify the rank 1 and rank 2 root systems. So, before that let me first introduce what is called this isomorphism of root systems. So, let us first recall the definition of root systems. Okay. So, a finite set phi of E is said to be a root system if it satisfies the following condition. The very first condition is 0 is not in phi and span of phi must be equal to E. The second condition, if alpha is in phi and C alpha is in phi, then we should get if and only if C equal to plus or minus 1. The third condition, if alpha is in phi, so then if you apply S alpha phi, then you should get back phi. The fourth condition, if alpha beta is in phi, so then if you look at this kata number, angle beta comma alpha, which is 2 beta alpha divided by alpha alpha, so this should be inside phi. So, these are all the properties of root system. So, now we say actually two root systems, they are isomorphic. So, naturally we have to preserve the properties 1 to 4. So, that means we need to have an isomorphism between these Euclidean spaces. So, let us call this phi comma E and phi dash comma E dash. So, these are all two given root system, and then we say this is isomorphic if there exists an isomorphism from E to E dash. So, not necessarily isometry, it is just an isomorphism. So, that means it is invertible linear transformation. So, this sense this capital phi onto phi dash, capital phi onto phi dash, such that, so these kata numbers when you apply phi, then it should be preserved. So, the kata number phi of beta comma phi of alpha, so this should be equal to, so beta comma alpha for each pair of roots alpha beta inside phi. If your if there exists such an isomorphism from your Euclidean space E to E dash, that mapping phi to phi dash, that preserving these kata numbers, then we say that these root systems, they are all isomorphic. So, let us see some consequences of this isomorphism. So, it is immediate that once we have this kata numbers preserving, then let us calculate what happens if you apply pi on S alpha of beta. So, you take pi and then apply it on S alpha beta. So, then you can see that this is going to be pi of beta minus the angle beta comma alpha alpha. So, that means this is going to be pi of beta minus the angle beta comma alpha pi of alpha. But since this angle beta comma alpha, the kata number associated with the beta alpha is same as the kata number associated with pi of beta and pi of alpha. So, that forces that this pi of S alpha of beta is equal to pi of beta minus the angle pi of beta comma pi of alpha times pi of alpha, which is S of pi of alpha of pi of beta. So, this indeed tells us that pi composition with S alpha is same as S pi of alpha composition with pi. So, that means this pi commutes with this S alpha. So, when you take this conjugate S alpha pi inverse, so then you get S of pi alpha. So, that is how it commutes. Okay. So, now this equation allows us to define natural isomorphism between the corresponding while groups. So, let us denote this W of pi to be the while group corresponding to pi and W of pi dash to be the while group corresponding to pi dash. So, then recall that W of pi defined to be a subgroup of GL of E generated by this reflection S alpha, where alpha comes from this phi. So, this is inside GL of E. So, now what we can do using this pi, one can define this pi tilde, which is a map from W of pi to this W of pi dash. So, this is given to be where you send sigma to just the conjugate of sigma under pi, pi sigma pi inverse. Now, using this formula, pi S alpha pi inverse is same as S pi alpha. You can see that this pi tilde map, so that is indeed an isomorphism. So, check that pi tilde is an isomorphism of groups. Okay. So, that way this W of while groups corresponding to phi dash, so they are actually naturally isomorphic. So, now what we want to do, we want to understand what will be the automorphism of phi. Okay. So, automorphism of phi will be again it is just an isomorphism of E to E. So, that is invertible linear transformations from E to E that satisfy these conditions. But using our lemma 1 that I proved in the last class, we can see that so this condition can be relaxed. Okay. So, let me just write down the result, then it will become clear. So, what I mean by the condition can be relaxed. Okay. So, here is this lemma 2, so which is can be used to understand automorphism of phi. So, here is lemma 2 in this chapter. So, what is the lemma 2 says? So, you start with phi being a root system, let be phi be a root system inside your Euclidean space capital E, and then the while group of this phi is denoted by W. So, if we take some sigma which is coming from GL of E, so that leaves phi invariant, okay, sigma of phi equal to phi. So, then we can immediately conclude that if we take conjugate of this S alpha with sigma, then we get S sigma of alpha. So, if sigma of phi equal to phi, so then one can immediately conclude that sigma S alpha sigma inverse must be same as S sigma alpha for all alpha in phi. So, in particularly if we compute this Cartan number beta comma alpha, so that will be equal to sigma of beta comma sigma of alpha for all alpha beta inside phi. So, this is the conclusion of this lemma 2. So, now let us see what is the immediate corollary of this lemma 2. So, in order to check the isomorphism between phi and phi, so that means automorphism of phi. So, we need to check that so this there will be a pi from this E to E that satisfying these conditions. Okay. But the thing is, if pi, if it is actually is an invertible linear transformation from E to E that sends phi to phi. So, then using this lemma lemma 2 we conclude that these Cartan numbers they are already preserved. So, that means we do not need to check these condition, this extra condition that we have here. So, this extra condition. So, indeed this lemma actually allows us to conclude that as an immediately corollary, if sigma is in GL of E, okay, sigma is an automorphism of phi if and only if sigma just leaves phi invariant. Okay. So, by definition, if sigma is automorphism of phi, then sigma must leave phi invariant, and we are saying that is also enough. If sigma leaves phi invariant, then using this lemma 2 we conclude that the Cartan numbers are preserved and this conjugations sigma S alpha sigma inverse must be equal to S sigma of alpha. So, this is somewhat immediate corollary of actually lemma 2, which is again lemma 2 can be obtained from the lemma 1, which I recall from the previous class. So, what is lemma 1 says? If you take a phi being a finite set that spans capital E, and all the reflections that comes from these elements of phi that leaves phi invariant. So, then you have let us say sigma in GL of V that leaves again phi invariant that fixes pointwise a hyperplane capital P of E and sends some non-zero alpha in phi to its negative, then the sigma must be S alpha. So, that is what we have seen. Okay. So, we will use this result to prove that our lemma 2, which is useful in understanding the automorphism of phi. Okay. So, let us start with sigma that leaves phi invariant. So, we need to conclude that sigma S alpha sigma inverse must be S sigma alpha. So, let us compute what is this sigma S alpha sigma inverse. So, here is the proof. So, let us compute this you fix this sigma inside your GL of E such that the sigma actually just leaves phi invariant. So, now compute sigma S alpha sigma inverse, how it acts. So, note that if you just compute this on sigma of beta, for any beta we get it is exactly equal to sigma S alpha of beta. So, if beta comes from this phi, then it is immediate that the sigma S alpha sigma inverse of this sigma of beta that will lie again inside phi. It is in phi if alpha beta is in phi. So, this is immediate. So, now just recall what it is to say that sigma S alpha act on beta. So, then using the formula of S alpha you can see that this is going to be exactly sigma of beta minus twice beta alpha divided by alpha alpha times alpha. So, which is going to be equal to sigma of beta minus twice beta alpha divided by alpha alpha times sigma of alpha. So, this is what the formula says. So, now if we take some element that is in sigma of p alpha. So, then you can see that this sigma S alpha sig inverse must fix that element. Okay. So, let some x is in sigma of p alpha. So, that means x can be written as sigma of y for some y in p alpha. So, now let us compute what happens sigma S alpha sigma inverse of this x. So, then you can see that this is going to be sigma S alpha sigma inverse x will be y, but y is coming from p alpha. So, S alpha fixes y. So, then we get this is sigma of y. So, which is going to be x. So, that means sigma S alpha sigma inverse fixes all the elements of this sigma of p alpha. So, note that sigma of p alpha is going to be another hyperplane. So, this is going to be some hyperplane, and we already seen that sigma S alpha sigma inverse indeed leaves this phi invariant, because if when beta varies over phi, then sigma of beta will vary over phi again. So, that tells us that. So, this is the first condition, this is the second condition, sigma S alpha sigma inverse of phi is nothing but phi. Okay. So, that means, so some of the hypotheses that are there in lemma 1 they are that are satisfied. So, this sigma S alpha sigma inverse actually fixes a hyperplane and it leaves phi invariant. So, all we need to check it actually kind of takes some non-zero element of phi to its negative. So, let us do this simple calculation and then see that a sigma S alpha sigma inverse when you act it on sigma of alpha. So, then what you get is exactly equal to sigma S alpha of alpha, which is going to be minus sigma alpha. So, note that sigma of alpha is coming from phi and it is non-zero because all the elements of phi are non-zero. So, this proves that sigma S alpha sigma inverse satisfies all the hypotheses that are there in lemma 1. So, let us go back to lemma 1 and then check all the hypotheses. So, you can see that, so whatever hypotheses that are there for this sigma is satisfied by sigma x alpha sigma inverse. Sigma phi is phi and it fixes pointwise hyperplane and it sends some non-zero vector alpha to its negative. So, all these hypotheses are satisfied for sigma S alpha sigma inverse. So, in particularly we can conclude that the sigma S alpha sigma inverse must be a reflection with respect to this vector sigma alpha. So, that means from this using lemma 1 we conclude that sigma S inverse S alpha sigma inverse is nothing but S of sigma of alpha. So, that is what we got. So, now using this formula we can see that already we did some computation. So, what is S of sigma of alpha of beta? So, you can see that S of sigma of alpha sigma beta is going to be sigma beta minus twice sigma beta comma sigma of alpha divided by sigma of alpha comma sigma of alpha times sigma of alpha. So, that means if you compute sigma S alpha sigma inverse of sigma of beta. So, then we have seen that this is exactly equal to sigma S alpha of beta. So, which is given by sigma of beta minus twice beta alpha divided by alpha alpha times sigma of alpha. So, these two things must be equal, and since this is equal for all beta. So, from that you can conclude that for beta in phi. So, you get this twice this sigma beta and sigma of alpha divided by sigma of alpha comma sigma of alpha must be equal to twice beta alpha divided by alpha alpha. So, that means the kata numbers corresponds to beta alpha and sigma beta sigma alpha, they are all same. So, from this we conclude that to check something is an automorphism of phi, it is enough to check it leaves phi invariant. So, now in particularly as an immediate corollary we can conclude that any elements of this while group W that will act as automorphism of phi. So, because if we take some sigma in W, so then naturally W is sitting inside GL of E, and note that this sigma also leaves phi invariant. So, that makes it sigma is actually defines automorphism of phi using lemma 2. So, this way you can identify W inside this automorphism of phi. Okay. So, this is a very important observation. So, later we will see that there are some other natural automorphisms that are sitting inside automorphism of phi. Okay. So, that will come from what is called this Dinkin diagram automorphisms. So, anyway that requires some more work. So, we will actually do that later. So, now I will define some more important notions related to root systems. Okay. After that I will stop. So, given a root system, so let us say phi E. So, this is a given root system. So, given this root system, one can naturally define what is called dual root system. So, what is dual root system? So, for that let us first define what is called dual roots. So, in a way this is actually corresponds to between T alpha and H alpha or alpha and H alpha. So, this is the kind of correspondence that we are trying to imitate here. So, if you think about it, what is H alpha? H alpha is given by 2 times T alpha divided by alpha alpha. So, alpha corresponds to T alpha using that like natural that killing form identification of H and H star. So, then this T alpha and H alpha, they are like related by this scaling. Okay. So, this is what we want to imitate. So, if we imitate this, then we get what is called dual root system. So, for that purpose, let us define this alpha check by 2 alpha divided by alpha alpha. Using the inner product, one can work inside E itself. So, there is no harm. So, then these elements will be non-zero definitely. So, then we can form this what is called pi check. So, you take E check to be capital E itself, no problem, and then you define this pi check to be, so those of this alpha, collect all this alpha check where alpha coming from phi, and this will be called what is called dual root system. So, dual root system of this phi. So, it is actually elementary to check. So, I will leave it to you to check that this phi check is indeed a root system. Okay. So, you have to check all the properties of root system. For example, 0 is not there and the only multiples are plus or minus alpha check, and then if you take this kata numbers, they must be integers, but that is again like if you calculate the kata number, you can see that they have close relationship with the kata numbers of original root system. And again reflections, so it is easy to see S alpha check must be equal to S alpha. In particularly, one can naturally identify the while group of phi check with phi. Okay. Using this, we can identify phi with phi check. Okay. So, we will use this natural identifications and all later. Again, so this dual root system will play a crucial role in the classification. So, again some of the properties are actually easy to see once you go to the dual root system and come back. So, whatever you know in linear algebra, for example, how the dual spaces are actually used, the same way in some sense dual root system also will be used. Okay. We can get many information about the original root system using the dual root system. Okay. So, I am running out of time now. I guess I will stop here and then I will continue in the next class with the smaller dimensional root systems and their classifications. Thank you.